who's going to talk about how to enhance hardware language in the age of LLMs.
Thank you for coming. My name is Renau. I'm going to be presenting what we are working on UC Santa Cruz with HDLAgents. So a little background on me. I'm a professor at UC Santa Cruz for a long time. My area of research is computer architecture. I even have students work on branch predictors. But really what I've been focusing, what it is going to talk about is how to improve productivity chip design. We've been doing work on compilers, new programming language, verification. But this is a little bit new touch. The work is done by two of the students, currently at UC Santa Cruz, Mark Zakharov, which is finishing now with a master's, and Farsanet, who is continuing with a PhD. And I have three new students who are going to be joining, three new PhDs joining to work on this project. So what is the goal, the high-level goal? We want to improve the chip design productivity using LLMs. So the LLMs are a new tool. So how can I use it to improve the productivity? And here I'm including coding, verification, frequency optimization of the design. This work is not to improve the EDA tools using AI. It's more like a front-end side, how to use the LLM tools. From a high-level point of view, so that we understand what I'm trying to do, is you can interface the LLMs in two main ways. One, you can use like a copilot kind of approach, in which the human drives the coding, and the LLM helps you to expand the code like a copilot. This is not what is worth effort, but this is not what I'm trying. What I'm trying is more no code where the LLM drives the coding. And the idea is because it has a potential for a much bigger improvement in performance. Both of them are reasonable approaches. I'm not sure which one is better, but I'm targeting the second one so that we know what I'm trying here. Now, if you get top-of-the-line LLMs like GPT-4, Cloud, things like that, what are the things that work? And you don't need much help. You write a simple test case. You ask, write me a Verilog wrapper with 5 corner cases over this problem. It will do a reasonable job. You write a system Verilog assertion. It will give you a good job reasonably. If you say some simple combinational only module, it will work. Now, notice that here in all those things are simple or very short programs. Whenever you start to go longer, it's going to have problems. So what is the state of the art not going to work? And what we are trying to fix. If you do some pipelining, that's not going to work, unless it's trivial pipelining. You try to optimize the design for frequency, not going to work. You do any complex work, we're going to see some of the things that fail as you scale. Forget about any design task. You'll say, yeah, give me this core. You say, yeah, here. But it's not realistic, not going to work. And one thing that we've been focusing in the beginning is like, because the only training they have is mostly with Verilog, many of the HDLs are like a small community, it's not going to work, so it's how to fix it. So that's one of the first things we're doing. And we are trying also to extract good documentation. Now, before we go over the flow and to showcase what's the problem, we can show it with a Python example. So imagine that you have this problem. Oh, the font size is very small for me now. So you just have the prompt that is a Python program in which you say, create a method called potato. It has a file name as an argument, and does not call any Python packages. And you need to read the markdown and return a string with all the header files, markdown header, the hash, in a string. So you give that to GPT-3, that's going to fail. So how do you usually, what we are doing is building an agent. So how will you improve on this flow to make it work? So it's something they call self-reflection, which is using an LLM to expand the code of the LLM. They call it chain of thought, or things step by step. There are several processes, several things, but mostly you interface an LLM with another LLM to expand and to refine the question. When you do this, you can get like a list of steps that it's going to have, and then you query again the LLM. But one thing that is kind of neat and we have this as an intermediate. So we give the problem in hardware, we create this step, and this becomes the spec of the code, so the human can check if it's OK on this, and then evolve the specification. Now, if I have this spec, it's going to be better, but it's still not going to work. So this example still fails. So why does it fail is because, well, how do we fix it? We put a human in the loop. So instead of going and debug the Verilog, we start to debug the spec a little bit higher level. And you expand the spec so that it has enough information. Now, there are going to be two things on the spec. One is a little bit LLM specific. When you try this example, at least with the version that we try on GPT, because it keeps changing depending on the version, it didn't work because the hash pound for the markdown can be indented. It's legal on the markdown syntax, but the code generated didn't expect that. So it didn't work. So you have to expand the spec, ignore headers in code sections, which can be indented. The other one is a little bit undefined on the spec. No matter what, the LLM will not have got it right unless just by luck. That in the output, I wanted to have a new line on the string. So you are going to have to iterate with the spec in the same way that you iterate with the program. But once you have that, so you start with the problem, then you do self-reflection to expand it, then you try to iterate with the spec. But in order to improve the behavior, usually when you build agents, there is two other steps. One is that you expand with context. Is this RAG that they tend to call is retrieval augmented generation. But there is also a grounding step. If you can do grounding whenever you're using any of those things, you should do it. If you are doing a chatbot, there is no grounding. But if you work in hardware design, we have a compiler. Compiler is going to check for mistakes on the code generation. You have a linter, you have a compiler, so that's a grounding step. So when you go the code, you generate, you ground it with a compiler. So what is the thing that we do? Is we compile the code when it's Verilog. Or we also do Chisel or other language we're going to see. So you iterate with the compiler. Now, because it might not know so much the language, so you expand every compiler error with some suggestions how to fix that compiler error. So you have a database of examples of how to fix those type of compiler errors. And then you iterate over the LLM. Now, after a few iterations, it tends to converge, but sometimes the LLM is not able to fix it, so then you go back to the human in the loop. So these are one of the three steps. You do self-reflection, you do context expansion, and then you do grounding. Now, one thing is that LLMs, humans and LLMs, both we do mistakes. So this is an example, just to, so you ask, when I was 6, my sister was half my age, now I'm 7, so it was 3, plus 1 should be 4. But many times they do mistake. You ask for a human in service stress, you might do a mistake too. So you always want to have a verification step. So what is the thing that we are putting, but it's not working very well? And let me tell you what. So you can ground using a verification step too. So what you do is you tell the LLM to create test bench, then you instantiate the Verilog with the test bench, and then you run it. You find failures, you go and iterate, fix the test bench, fix the code. If after a few number of iterations, the thing does not converge, then you go back to the human in the loop. This part, I'm not going to show results because it's not working as well as we want. Let me give you the intuition why it's not working. One is because we are using the same LLM for the code generation and the test bench. As hardware designers, we know you don't want the same person who does the code who builds the test bench. You want to have a designer who does the specification, another designer who reads the specification and builds the test, another designer who builds the code. The same problem is happening with LLM. It has the same bias. It misunderstands the spec in the same way, and the test bench and the code are generated with the same problem. The thing we're doing now is using different LLMs for different parts of the problems because they have different biases. In addition, one thing that we try with fine-tuning GPT-3, but it's not working very well, is that whenever you have a compiler error, you have to fix it. And fixing from Verilog code is not working so well because it gets confused with the waveforms and pipelining. So this part I'm not going to show you because it's still a work in progress. So what I'm going to be showing results is for the upper part, that's working fine. So it's what we call the HDLAgent. It's a GitHub repo, it's open, even though we don't document it much. I'm going to talk about that. And it has 3 steps. There is self-reflection, there is context, there is grounding. So how does it behave? So this is data that we gathered like 2 months ago. So it's an older version of GPT, and we have expanded the benchmarks, but in comparison with the next plot. But what we have here is 4 programming languages. We are trying with the GPT-4, the best LLM for this plot. We tried many LLMs, but that's for the best. For this plot, it's the best LLM. We have Verilog, Chisel, PyRTL, DSLX, and there are 2 types of benchmarks. HC is HD eval combinational, so it has combinational only logic, and HP is for pipelining, because it performs much worse when we do pipelining, and we're going to see as we expand the benchmarks. This set of tests, it was mostly based on the HDL bits, in this version here, which are very simple website for how to teach programming Verilog. We convert it to be generic to any programming language. So it tells you, do a shift left and pick the bit number 3. So those kind of things, simple examples. Verilog high success rate, Chisel, it's decent, but you try something like DSLX, doesn't work. So as we apply the HDLAgent, first thing is that you provide context on the language, and there is some suggestions, how do you build this context, but mostly you have to summarize the language. Don't provide the whole tutorial because it doesn't perform so well. You summarize the language, and then you provide a few examples. So with this, you are able what they call knowledge transfer. So you don't need to fine-tune the LLM, or you don't need to create a new model for a language that doesn't know. It's able to transfer knowledge from one programming language to another. So with very few examples, around 8,000 contexts, you can build it. In addition, you can put a compiler that will catch more errors. It's nicer if the compiler can provide errors that are LLM friendly, so that then it can catch up more the typical mistakes. And then you can provide hints how to fix some of those errors. So this is for an older version of the flow that we have, older compiler. Now what we have been trying different LLMs, and we have improving the flow. You notice, you think about here what we have is success rate. The benchmark is the same as before, but we pick from if fabless many of the competitions. They were having competition for using GPT. So we pull the prompts, we clean it up, and we put it as part of the benchmark. And then we classify as combinational pipelining. Because the people who were doing those competitions know that GPT was not working very well with pipelining. Many of them were doing just combinational queries. So that's one thing that is different on the benchmark from comparison with before. But also on the x-axis, we have many different LLMs. Here, the target is only Verilog. I have data with many other languages, but no, it's no time. So what is the thing that you see? First is that the HDLAgent is able to crank up the performance for the LLMs that don't work so well. Like we tried Mixtral, the MOE, the 8.7 billion. The last one, the 22B, was released just 1 week ago. And we're able to get the benchmarks and running. That one, I have some hope they will get better because it was released 1 week ago. There's still no fine-tuned versions to follow instructions. But even without the fine-tuned version to follow instructions, able to get it up and running. But clearly, you have to have a description. You have a few shots you have to have compiler feedback and fixes. So this is the overall results of what you can get. You can get a not so performing LLM to improve. It's not going to match the top performing LLMs. But across languages, that is what it was in the previous plot, you can get the same LLM across all the HDLs to perform more or less the same. And so that is an important contribution is that you are building your own new programming language. You don't need to worry, oh, now I have my new programming language. No one is going to be able to use GPT, whatever version, with my language because it's new. It does not exist. So in that way, you can provide some context, provide the flow, and people who are trying to learn about your language can use it and have queries and evolve. And the LLMs are extremely useful for learning a new programming language. So what are some of the challenges? What are the things that they are not working? So the current LLMs cannot handle very large designs. So what we have here is the success rate. This is very low. And the y-axis is the output tokens. The problem is not the input of the problem. The problem is the output of the problem. So you are very verbose. That's great. The problem is like how complicated is the program that you have to generate. Tokens more or less like a word. It's not exactly the same, but it's like a word. So it's the number of words that you have in your program. Clearly, you see a trend going down. Some like GPT-4 handles better up to 500 and then falls down very fast. That's something that I'm hoping, because it happens across other languages, hoping that the community will help in other languages and then will just automatically leverage. Otherwise, what it forces you to do is to have very small code blocks when you structure the code. But you use a small code blocks, small functions, then it's reasonable. Another interesting insight is when LLMs need compiler errors. And you can do compiler errors that are more friendly for the LLM or not. So this is an example of a very simplified example of PyRTL error. So what happens on the output, it has input, XOR, the input shifted right. This is a compiler error because it's using a shift right, Python shift right. It's a DSL, so that shift right is not the PyRTL shift right, it's the Python shift right. So you mix these two things, it's a compiler error. If you generate a decent compiler error to the LLM saying, in this line, this shift right is a Python, you should use this other thing, it will go iterate and fix it pretty fast. But if you just say syntax error, no line, it's going to have a hard time. So reporting line of code, reporting what's the message, and a hint of what's the problem, that will help a lot. It helps a lot whenever you have those fixes. The justice is great, but it's not great reporting the type of error that we have. If we use slang, for example, it's better to recover errors because it has a better warning system. One thing that we still don't have a clear answer is how do you write the spec? This is one of the test benches that you have SHA 256, and you can have the verbose English on the top right, which works, generates the code, but don't tell me to debug that paragraph in English because I prefer to write code than to read and debug that paragraph. And things that you can think the LLMs as context-sensitive compilers. That's another way to see them, in the sense that when all the programming language we have is context-free, they have to be very strict. Now I can write the bullet list on the left. That's more readable, more understandable. I can even have a Python program and say, but this input has 12 bits, and then write some English sentence in between and say, translate this to Verilog. All those options work. It's not clear for me what's the best. It depends at the end who is going to generate that spec. It's going to be a human, or we're going to have a step on the LLM who generates that spec. If it's a machine generating that spec, well, I don't care if it's verbose like the top. But if it's a human, I don't want that English. That is what most of the benchmarks are now. Most of the benchmarks are horrendous paragraph like that they are correct. You don't debug it. It's like the example I was having that the prompt was under-specified. They are correctly specified. So clearly there is a problem with the benchmarks that we have to fix. Even as a community, it's not clear for me what is the format of the prompts that I want to have. So some surprising shortfalls. The LLMs are extremely lazy, but with long tasks. If you just have unroll a loop, and it's simple to unroll, it's just repetitive. It will not do it. It will just put dots in between, let's say, and continue. You finish it. So things that you will think is like, oh, the machine can do that, is the things that is going to fail the most. So it's going to have a hard time with those things, so you have to be careful. So it's unable to do any code planning design. I know some faculty who are working on this. So this is a problem that exists in Python too. So much bigger community, I think they will fix it. I'm not focusing on that, but that's clearly a problem. It's quite bad at pipelining. I'm looking at that. So we had tried a thing, it didn't work. Now we try another thing, hopefully it works. But currently, you try pipelining, it doesn't work. And it's unclear what's the spec. Now the roadmap, and that's the finished slide, is we're trying to expand the benchmarks. We're trying to finish text verification, fix pipelining. They have several steps. The code is available on the GitHub. I'm making it public. You are welcome to contribute. But currently, it's very paper-driven, so not very friendly. But the idea is that we want to improve, and it's open. It's Apache license. You can use it. You want to contribute, that's great. And so that's the conclusion. The only thing I wanted to have a funny example. You might have little issues if you try. Like, for example, when we tried GPT-4, G Pro, you put the prompt, say, generate the Verilog, and suddenly we start to lose a lot of benchmarks. Like, why is it not generating results? And it's because they categorized as dangerous. Verilog was dangerous. So content. So suddenly it's not generating output. So you are going to have to suffer some of these little things. So now we, for example, G Pro, we fix it. Gemini Pro. But you are going to have little issues like that. Hopefully we clean up and it becomes more user-friendly. So that's the thing. You have any question? I don't know if I ran over the time. If not, we can talk after.
Thank you. I think we have room for one question. We gave that to Matt.
Yes.
Thanks. So it seems like the biggest improvements you got were by explaining the language to the LLM.
And the compiler grounding, the three things.
Sure. In terms of the bars, though, did you do that via fine-tuning or more of
No, this is not fine-tuning. This is using all those models without.
Okay.
We have tried fine-tuning for fixing the Verilog, the test bench side, but it's not really working.
So it's
so the fine-tuning didn't work so well.
Thank you.
Thank you again, Jose.